If we look at the portfolio optimization, the portfolio is basically the optimization of number of assets. So we'll be given a number of assets. And in this case, we'll basically select the subset of the assets and their weights in order to basically find the best portfolio. And we'll define different ways of defining the best portfolio. So in the outline, we'll start with some primer on financial data. Then we'll talk about some modeling the returns and the portfolio basics. Then we'll discuss some of the heuristic portfolios that are used and performs quite fairly in practice. Then we'll continue with the Markowitz portfolio theory, which is the one that we are mainly used. There will be different types of portfolio related to this Markowitz modern portfolio theory, and known also as MPT. And there will be different portfolios with their abbreviations that we have seen. We'll then see risk-based portfolios, and then we'll compare the portfolios in this lecture. So in this case, if we look at some primer on this financial data, so in financial domain, so the log prices rather than the prices itself is kind of models a random walk. So this is one of the assumptions. So assume that let's PT be the price of the asset at times T, and let's assume that the YT is log PT. So logarithmic value of the asset price. And the asset can be anything. So it can be a bond, it can be in most of the cases equities, it can be cryptocurrency. So it's asset is basically a thing that you can buy and sell in the market, and it has a value. So in this case, we use the logarithmic prices, because in this case, basically the logarithm of prices models a random walk. And the model here will be something like YT, which is basically logarithmic price, log price at time T, at time T is equal to some mean drift. So this will be the mean of this, basically the price. So this is mean plus, or this is the mean drift. So it's basically the mean addition to the log price at the previous time step. So this is y t minus 1 is log price at t minus 1. And we have some Gaussian node epsilon t here, which is Gaussian noise. So log of these prices can be modeled as random walk. And the distribution, it's this is the assumption, basically Gaussian noise. In general, this is not fully true. The randoms are not random walks, and because the random walk means it's not known, so you don't know whether it will be basically up or down or which location it will be, because there is an epsilon t component in this basically the equation. But however, the markets are known. Even though the markets are known, the fundamental model assumes that basically log prices makes a random walk. In this plot, you basically see a time series. So starting from the 2007 up to 2017, so we have basically S&P 500 index prices. So S&P 500 is an index basically, which is made up of a number of assets. So this is also referred as market. So people say, for instance, market is up when S&P 500 increases, and people say market is down. When this S&P 500 decreases, it's kind of a representative index of US market. And again, the log prices is assumed to do a random walk. And asset log prices as a result basically assumes to do a random walk. And again, basically stocks, we are using the returns to model in many cases. So there are two things to model. First, we can use prices to model basically our time series. And the second thing is we can use basically the returns for our purposes. And the returns are basically used for modeling because they are kind of stationary. So if you look at the time series properties, they are known as stationary, meaning that basically stationary has the main definition is basically property of these time series is same across time. So for instance, covariance matrix and basically the mean value at some t point is same as the mean value of this time series and its covariance at another time point. So we'll see during this course what you mean in detail by the stationary in next lectures. And again, the return is basically, simple return is basically just price PT minus 1 divided PT minus 1. So for instance, if the price is 100, then it becomes 120. Then this means basically a 20% increase. So this is basically a simple return. And another thing is basically a log return. And the log return comes from the basically the exponential complexity. So in this case, we have this PT is equal to PT minus 1 and times e to the r, which is this exponential return. And in this case, basically, then the return, the exponential return is basically becomes log of these prices. So it's basically comes from the continuously compounded return. Then here is PT, the price at time t, price at t time minus 1, and exponential or exponentiation of r, where r is the return, as you see here. And in this case, if we take the logarithm of both sides, then RT becomes basically log of PT divided by PT minus 1. And again, which is in this case, log return is related to the 1 minus simple return that we have calculated here is equal to RT. And again, in this case, the log return is basically stationary. So if you look at the log return, then it's basically the yt minus 1 is equal to some mean mu plus basically the epsilon error that we have seen here. And again, this is basically stationary, meaning that it has a constant mean independent of the time that we are observing. And its covariance matrix will also be made up of these, it will come from these matrices, multiplication of these entries, and it will also be constant over time. And again, for smaller values, basically log return and simple return are same. So yes, you can.
When we talk about mean, what is the data? I mean, when I'm thinking about a time series is almost indefinite, right? Like it's infinite.
Yes.
So when we're talking about the mean, what do we mean by that? Like, what is the interval?
Mean is the drift of this process. So it's basically the mean drift of the market. So even though the time series is infinite, and we are considering finite here, but we can assume it's infinite, then the mean is the mean drift. So mean drift in this basically the equation here. So it's the expected time the prices or the return changes from one point to another one. So if the market is going high, so for instance, in many cases, the market is always increasing. So there is an increasing trend. That's why this basically mean is positive.
Thank you.
Hopefully that answered your question. But again, things become more complicated and more theoretical when we think about infinite time series. So again, if you look at the log returns and simple returns, they are basically same. For smaller values, they are almost same. But for if the return values tries to grow in either side from 0, then basically log returns and simple returns kind of becomes different. And here we have S&P 500 log returns. So again, S&P 500 is an index of the US market. So in this case, if you look at this time series starting from beginning of 2007 and up to the end of 2017, that's how the market looks like, the log return looks like. So if you notice here, so during the crisis, so in 2008, end of 2008, if you remember, there was this big market crisis. In this big market crisis, the market was quite volatile. So that shows how the market looks like. And again, this is quite different than in this case than for infinite time series. Then the process or single mean assumption will violate because the markets are not random walk if you look at infinite point of view. But if you look at certain time series, certain subset of time series, then the markets are basically doing some sort of random walk so that the next time step cannot be easily predicted. So volatile market, and in this case, this is due to 2008 crisis. And again, if you look at the other time points, then basically there are some increases and decreases in 2010 and 2011 as well, but they are not as volatile as in the end of the 2008. And in terms of the log return, this is how the S&P 500 index looks like.